Alright, hello everyone. Welcome to this AI for OPT lecture series given by Jiamin Xu. Jiamin is an associate professor in the field of business school at Duke University. Previously, he was at Purdue Business School before Duke, and he received his PhD from University of Illinois, and before that, an MS degree from UT Austin, and previously a bachelor's degree from Tsinghua University. The awards he received include a Simon Berkeley Fellow in 2016 and the NSF Career Award in 2022. And Jiamin is an expert in high-dimensional statistics, especially statistical problems in random graphs, which is the main topic of this lecture series. So in lecture one, we'll be talking about the planting matching problem. So welcome, Jiamin. The floor is yours.
Okay. Thanks, actually, for the nice introduction. Can everybody, is that okay? Can you hear me? Okay. So it's very my great pleasure to actually visit Georgia Tech again. Yeah, like in this lecture, I'm going to focus on the planting matching problem. But before I get started, maybe I can tell you a little bit about like the motivation of this, and also give you an overview of this entire tutorial. Okay. And also, just want to say that just feel free to interrupt with me. I'm actually primarily going to use the slides for my presentation, but I will, if there's needed, I will actually try to explain to write on board. So yeah, let's see how it goes. Okay, so the motivation for this tutorial is that in many like modern data science applications, we often encounter some so-called planted problems where we have some like optimization problem, but with some good solution already built in. But this good solution is actually obscured by the noise. Now the question is that, can we recover this good solution based on the noisy observation? Okay. So one of the prominent example is actually this community detection problem. So you can see that in this picture. So this community partition actually give a good like partition of the network into different parts, so that there are more edges within the community and there are few edges across communities. The question is that you do not observe the underlying community, but you only observe the networks, and then can you recover these underlying communities? Okay. Okay, there are some other classical examples. For example, you can also consider the so-called planted clique problem, where basically there is that you have some like a hidden clique embedded in some large random graph, say Order-Shen random graph, and now your goal is to recover this hidden clique. Okay. The third example is actually the clustering problem in mixture models. Okay. So the common theme of these classical planted models is the underlying low rank structure. So if you look at the observation matrix, like if you put the data or the adjacent matrix, often this is approximately low rank. And it turns out that this low rank structure is actually the underpinning of many phase transitions observed in these kind of problems. So I don't know if you still remember, so Sabarabarat from Sam from Harvard, so he actually gave a tutorial last November. So he actually talked a lot about this kind of problem. He mentioned about this computational statistical phase transitions. And then I think he also covered some spectral methods and semi-definite program relaxations. So lots of this algorithm, the underlying idea is also kind of based on this low rank structure. Okay. So in this tutorial, what I'm going to focus on is actually a new set of planted problems. So in this, it's also kind of driven by the applications. In fact, in this lecture, I'm going to focus on the first one called planted bipartite matching problem. So I'm going to tell you more in detail later. But at a high level, you can imagine you have a bipartite graph. There's a hidden perfect matching on this bipartite graph. And then you have some noisy observation of it. And now your goal is to recover this hidden perfect matching. Okay. Another example that I'm going to cover in this tutorial is called graph matching, also known as network alignment. Basically, in this case, instead of one graph, you have two graphs. And there's some hidden vertex correspondence between the vertices. And now you have some correlated edges between these two graphs. And now your goal is to recover this hidden vertex correspondence. There are some other examples that I won't cover in this tutorial, but they're also very nice and very natural. For example, you can possibly plant some other subgraph structures beyond like the clique or partition. Like for example, you can try to consider the so-called Hamiltonian cycle. So you have a Hamiltonian cycle embedded in this large order Chern random graph. And then again, you have some noisy observation. The goal is to recover this hidden Hamiltonian cycle. It's actually related to the traveling salesman problem as well. You can also consider some other structures like the trees. K factors are actually so-called, it's basically the spanning K regular graphs or the so-called K nearest neighbor graph. So you can actually play around with it by plugging your favorite subgraph structures and then try to come up with a model to see when you can recover it from this noisy observation. So the list actually continues to grow, I would say. But one thing I want to emphasize is that the common theme of this kind of new set of planetary problems, in contrast to the previous examples, is the lack of this low-rank structure. So I will show you later that often in this kind of problem, if you look at the observation or the data matrix or the JSON matrix, they are not, so they don't actually have low-rank structure anymore. And then because of that, for example, some like straightforward spectral method won't work anymore. Because the spectral method actually, for that work, you need to have the low-rank structure, so then you have some so-called eigengap, so then the method to be robust to some noise. But then if you don't have the eigengap, then the method is very brittle to this noise perturbation. So that's why for this set of problems, it brings like new challenges in both statistical analysis and algorithm design. So that's going to be the focus of this tutorial. So in particular, in this tutorial, I'm going to focus on two problems. One is this planted bipattern matching problem. You can also view this as so-called planted linear assignment. I'm actually going to show you later. The second topic is this graph matching, also known as network alignment. So this is actually, you can also view this as a planted quadratic assignment problem. Okay, so for those two problems, I'm going to show you like the new analysis needed for this, and also the new algorithm design ideas. Okay, so this is actually the specific topics going to cover in the 4 lectures. So in this first lecture, I'm going to focus on this planted matching problem. In the second lecture tomorrow, I'm actually going to talk about the random graph matching, focusing on the information-theoretic limits. Okay, so the first 2 lectures are actually going to focus on the statistical analysis. So I'm going to tell you like what the new tools or new ideas needed to do this. And now in the third lecture, I believe that's on Thursday, so we're going to talk about efficient algorithms for random graph matching. And then on Friday, I'm going to talk about some new ideas from the so-called low-degree polynomial approximations and also the local algorithms. Okay, so the last 2 lectures are actually going to focus on the efficient algorithm design. Okay, so that's basically the overview of this tutorial. Any questions before I keep going? Okay, good. Okay, but before I get started, I want to motivate a little bit more of these assignment problems from this operational research perspective. Okay, so like this assignment problem is actually very common in operational research. It's kind of arguably one of the most fundamental optimization problems. The problem actually was introduced actually back in 1957 for these so-called facility location problems by actually the Koopmans and the Beckman. So it is worth noting that Koopman actually won the Nobel Prize in economics in 1975 for the work related to this on this resource allocation. So basically, at that point, they actually look at this very simple facility location problem. You have a bunch of factories on the left-hand side. You have a bunch of locations. And then you can imagine there's some different operating costs for assigning a particular factory at a particular location. And now the goal is to find the so-called best assignment to minimize the total operating cost. Okay, so you can formulate this as a simple linear assignment problems. The pi ki equal to 1 if you assign factory k to location I, otherwise it's 0. And then this objective just computing the total operating cost under this particular assignment pi. And you want to find the best assignment. Okay, so here if you view pi as a matrix, this is the permutation matrix. And then you know that the convex Hall of the permutation matrices give you these so-called doubly stochastic matrices, right? So that's why this problem can be efficiently solved by using linear programming. Okay. So in this paper, this is actually one of the possible, like the optimal solution. in this paper, they also consider more complicated scenarios where they're going to take these so-called transportation costs into consideration. So here you can imagine you have these different factories. You have some products you need to transport from one factory to the other factory. So the BKL is actually the units of the product needs to be transported. And now CIJ is basically the cost of the transportation cost, like per unit. Okay, and now this time you still want to do the assignment, but now you want to minimize the total transportation cost. Okay, so here, now you need to introduce two permutation. So here means that if you say assign K to location I, and then factory L to location J, then you're going to pay BKL times CIJ. Okay, and then you sum up all the pairs. So that's the total transportation cost. And you can see that in this case, the objective function is a quadratic function of these permutation like matrices, right? So that's why this problem is called a quadratic assignment problem. And it turns out that this problem is actually much harder. I mean, we know that nowadays this is NP hard in the worst case, but back at the 1957, so very interestingly, if you read the paper, the last paragraph, they comment that so they actually found this problem very hard, so they couldn't find efficient algorithms, so they actually delayed the publication of the paper just in hoping of getting a better algorithms. Okay, but then at that time, there was no notion of NP hardness, so that's why they don't know about this. But nowadays, we know that there's no efficient algorithm in the worst case. Okay, but that's just some interesting story that I want to share with you. But in this tutorial, I'm not going to focus on this optimization perspective. I'm going to take a different, more statistical perspective in the sense that I'm not really interested in finding the best assignment per se. I'm interested in there's some hidden assignment already built in the solution or in the problem, and now have some noisy observation. My goal is to recover this hidden assignment. Okay, but you can see that these two kind of perspectives are still related. Okay. Okay, so I think that's the overview. And now I want to actually go into the details, focusing on this planted matching model. Okay, so that's going to be the focus of this lecture. Okay, so let me actually first formally describe the planted matching model. So it's actually a very simple model. Later I'm going to tell you where this model comes from in applications. So basically, consider you have a bipartite graph. You have left nodes, and then you have right nodes, right? And then the edges actually are weighted, okay? So here you have some hidden, perfect matching, M star, actually denoted by these red edges. They are crossing straight, but this is just for a simple illustration. So you could actually have perfect matchings in different ways, right? Okay, now for all the pairs that are not on this hidden perfect matching, they're going to connect it with probability D over N. Okay, so D over N. So basically, all these blue edges, they're actually drawn with probability D over N. Okay, so roughly the average degree of the blue edges, like the number of incident blue edges for a particular node, is roughly D. Okay, so you should imagine that for every node, you have 1 edges on this perfect matching. You have roughly D edges not on the perfect matchings. Okay. And now on top of the edges, you also observe some weight. So they're going to follow 2 different distributions. So for all edges on the perfect matching, they follow 1 distribution P, I, D. And then for edges not on the perfect matching, then the weight is drawn according to different distribution Q, again, independently across all the edges. Okay. So now the question is that you do not observe where are those hidden matchings. The goal is to recover this hidden matching M star just based on the edge connections and then the edge weights. Okay, is the problem clear? Yes?
Do you think of D as a function of N?
Yes. So later I'm going to show you that D can possibly depend on N, but D can also be a fixed constant. Yeah, so yeah, I will talk more about that. And also, just to give you a little bit of intuition, right? So definitely, this recovery problem will become harder if D is large, right? You have more this confusing blue edges, right? And also, the problem gets harder if P and Q, these 2 different distributions, get close, right? So it becomes harder to distinguish like where are those like planted edges, right? Okay, so later you will see that the statistical limit for this recovery problem going to depend on this parameter d, and then some distance measure between p and q. Okay, makes sense? Okay, so before continue, let me just tell you one interesting motivating application, like where this problem comes from. So this problem actually comes from this so-called particle tracking. So you can imagine in many like applications, you have a bunch of like objects, they're moving kind of crazily in space. So for example, like in biology, you could have this swimming microbe, right? And then you're going to use this microscope and then try to track like how this microscope actually going to move around. Okay, so how to do that? Often what they do in practice is that they're going to take a sequence of video frames, right? And then for each 2 consecutive frames, you want to actually recover the correct correspondence between the particles in the first frame versus the next frame. And if you can do this for every 2 consecutive frames, then you kind of recover this entire movie trajectory. Okay. So this plot actually show you these 2 frames superimposed on each other. So the red dots here actually are the particles in one frame. And then the blue dots actually the particles in the next frame. Like they move a little bit, so they are moving to the new location in the next frame. So I put these 2 frames together. So that's why you see these kind of blue dots and then red dots. Okay. On the right-hand side, I actually show you the ground truth, like the true movement. Okay. You can see that, for example, this particle actually moved to this point in the next time, right? Okay. So you can imagine this problem can be modeled as a Ponte matching problem in the sense that like the red dots actually are the nodes on the left-hand side in this bipartite graph, and then blue dots actually are the nodes on the right-hand side, right? And now this correct node correspondence is actually this true like hidden perfect matching that I want to recover. And then the edge weights, you can think of there are some distance between the particles in the red, like the red particles and then the blue particles. Make sense? So that's why, so that's actually where this Ponte matching come from. So they actually, it's actually this first paper proposed this model for particle tracking is actually this PNS paper back in 2010. They actually consider a very specific model choice. Because they want to do some analysis, they actually pick d equal to n. So back to the model, that means you have a complete weighted bipartite graph. And then the distribution for the edge weights on the like planted edges, this is like the absolute value of a Gaussian random variable with 0 mean and then the variance kappa. Okay. And then the Q is the distribution, like the edge weights for like the edges not on the Ponte matching, they assume is the uniform between 0 and n. Okay, so one thing I want to emphasize a little bit is that why they pick this specific scaling, like why they put n here, is because if you look at a particular particle, it will have like n minus 1 confusing like locations. And then if you look at the minimum of this distance to like n minus 1 fake matches, so that is like you have n minus 1, like so you basically have a minimum of n minus 1 IID uniform. So then that minimum should have a scale roughly on the constant order. So that is kind of comparable with the distance that you will see for the true pair. Okay, so that's kind of the challenging scenario that you will have some confusion. Does it make sense? Right? So basically for every particle, you have n minus 1 fake matches, right? And then you look at the minimum distance among those n minus 1 fake matches. So that distance should be on the order of constant 1 because of this scaling. So that's the same order as this distance to the true match. Yes?
So the bipartite graph you have on the previous slide is,
yes.
How does it correspond to the next problem? Is basically that each weight is the distance between the
yeah.
points.
Yes, that's right.
Blue and the red point, and therefore here really Q has a larger scale.
Yeah, exactly. Very good. Yeah, so that's exactly the case that I want to mention, right? So Q, this is a thing about this is a distance, right? Uniform between 0 and n. So the typical distance is much larger. That makes sense, right? If you look at a particular particle, so it probably won't actually move very crazily to the other particle, right? So that's why the distance is on the order of n. Okay, but if you look at the minimum distance, so then that's only the same order as the planted edges. So, yes, question?
So how does this relate to your question about low rank? Are you trying to say like if the weights are low, they kind of corresponds to that those edges are kind of not there, and that's what acting as low rank proxy?
Okay, so here, so I didn't emphasize that, but here what I mean by missing of low rank is just basically look at this W as a matrix, and then this matrix probably is not low rank, right? So for example, exactly like for in this case, D equal to N, so you have this so basically your data is just this edge weight is an N by N matrix, right? And then the edge is either P or Q, and then there's no low rank structure. So that's what I meant. There's no low rank structure for this problem.
But if some of the weights are like really high and some of them are like really low,
yeah,
then you can still.
Yeah, so you can still try to recover that. So that's the reason why you can do that. But then the rank of this matrix is still high. It's actually a 4-rank matrix, right? Yeah. Yes.
So the uniform zero, and I understand the explanation you gave from the planted matching perspective.
Yes.
But from the application perspective, is there a reason why it should be uniform?
No. Yeah, there's not really very strong like practical motivation. The reason why they look at this back in 2010 is because this is some nice choice. They can do some analysis, give some precise prediction. That's actually something I'm going to talk about next. But later I'm going to show you our result actually do not really depend on the choice of P and Q. It's just an example. They somehow choose in their application. Yeah.
Thanks. Is this copper related to temperature or something?
Yeah, I think that maybe, or it relates to, yeah, I mean, if you really talk about the practical application, yes. This also depends on, in fact, this also depends on how fast you're going to take these 2 consecutive images, right? So if you take faster, then the particles tend to move just a little bit. And then it also depends on the noise of the camera. So yeah, there are many things. Oh, in fact, this is actually a good point. So I should have mentioned that in this tutorial, often the case, I will give you some motivating application, but I won't actually go into details. So I'm going to focus on the theory part. But there are actually a very nice application, I would say that. So if you're interested, there are some references that were given. And also sometimes we indeed apply the algorithms we develop to the real application. So we're going to talk a little bit about in the last 2 lectures. But most of the time, yeah, I'm going to focus on the theory side. But that's, yeah. But yeah, so yeah, feel free to ask any questions about application. Yeah. Okay, so this is actually so this is actually how I get into this problem. So I just want to tell you a little bit of the history behind this work. So basically, when I read this paper, I actually noticed that they actually make this very kind of a shocking prediction. So they basically, so they call this a random distance model, by the way. And then they actually have a precise prediction about how large this kappa, like this noise, like variance, needs to be. So then the maximum likelihood estimator going to coincide with this true permutation. So they basically say that when this kappa is less than this threshold, like 0.174, okay, so then they predicted that if you look at the maximum likelihood estimator, they're going to coincide with this true one. In fact, what they really meant is that the fraction of edges that misclassified actually going to 0. Okay, so you kind of almost correctly identify all the edges on this planted matching. On the other hand, if this is bigger than this threshold, then actually they predicted that so they're going to misclassify a constant fraction of the edges. Okay, so you can see that this is like some precise prediction of the phase transition threshold. Okay, so in fact, later I'm going to show you that based on our rigorous theory, so we actually show that the optimal threshold is actually not exactly 0.174, it's actually 0.159. Okay, but that's, yeah, I mean, that's how I got interested in this kind of problem. Yeah, so at one time, we were really trying to push to get closer to this 0.174, but later we figure out this correct one is 0.159. Okay, it's actually 1/2 pi, basically. Okay, okay, sounds good. Yes, it is sharp. Yeah, so that's what we're doing here. Yeah. Okay, so now let's actually talk a little bit more about this problem. So let me tell you like how we get get this result. And then actually, like as I said, our result is actually holds for more general distribution P and Q. Okay, so a good starting point in all this kind of problem is actually always like to look at this maximum likelihood estimator, right? So for this problem, it's actually not that hard to write down the maximum likelihood estimator. Okay, so basically, like you will have, I mean, if you look at a likelihood ratio function, you're gonna see like bunch of P for edges on the matching and Q for edges not on the matching. If you do a little bit of algebra, you will see that if you want to maximize likelihood, you basically want to maximize this log likelihood ratio. Okay, by searching over all the possible matching. And this is actually a maximum weighted matching problem. Okay. And then since matching, you can also view this as like a permutation, right? So this is exactly a linear assignment problem. And then as I mentioned earlier, this linear assignment problem can be always solvable in polynomial time. Okay. So in some sense, there's no kind of computational issue here. But then the question that we're interested in is that how accurate this maximum likelihood estimator is. For one thing that I want to mention is that for certain distributions, actually this log likelihood ratio can be simplified. So for example, if both P and Q are just some exponential distributions, and then you can actually simplify that in the sense that if you maximize the log likelihood ratio, this just becomes minimizing the weight. Okay. Now the question that we're interested in is that if you compare this maximum likelihood estimator with these ground truths, like the true matching M star, how much they have in common. So in particular, in this lecture, we're going to focus on this measure called overlap. It's basically just computing the fraction of edges that are shared in common by this maximum likelihood estimator and then true matching. You can also view this as 1 minus this 1 over 2n times this expected value of this cardinality of the symmetric difference. Right? So basically, the symmetric difference just calculates what's the total number of edges that are misclassified by the maximum likelihood estimator. So sometimes I'm going to call this as an error, like a reconstruction error. And the overlap is basically 1 minus the reconstruction error. Make sense? OK, and now the question that we're interested in is that what is the information theoretical limit for this reconstruction problem? Like in some sense, like when this overlap goes to 1, and then when this overlap actually is bounded away from 1. So you will see that this actually depends on the 2 parameters. One is this average degree D, okay? And the other is some similarity measures between P and Q. Okay, so in particular, it turns out that the right similarity measure between P and Q is given by this so-called Bhattacharya coefficient, also known as Hellinger affinity. Okay, so in particular, the definition is given by the integral of the square root of dp times dq. Okay, so you can see that, for example, when p is equal to q, then this integral will give you 1, right? So that makes sense. When p and q are the same, the affinity is 1. Okay. On the other hand, if p and q are kind of mutually kind of singular, then this integral will give you 0. So in that case, p and q are very different. Right? Okay, so now let me talk about our main result. So the first thing is that we can show is that when the square root of this average Breuil degree d times the Bhattacharya coefficient between p and q is less or equal than 1, then actually the overlap between the maximum likelihood estimator and the true matching actually goes to 1. Okay, meaning that if you look at the maximum likelihood estimator, so the fraction of misclassified edges actually goes to 0. Okay. Conversely, we also can show that when this square root of d times Bhattacharya coefficient is bigger or equal than 1 plus epsilon for some fixed constant epsilon, then for any estimator m hat, the overlap is actually bounded away from 1. It's actually bounded away, it's upper bounded by 1 minus c, where c some constant depends on this epsilon. Okay. So the converse result actually holds for both these two settings. One is this sparse model where these D and P and Q, they're all fixed. So they do not actually scale with N. Okay. Or they also hold in the dense model where D actually grows to infinity as N go to infinity. So the kind of the graph is denser. And now for this to make sense, the density for this Q is actually has to scale in this way. The reason why we scale in this way is precisely the same reason as I explained earlier for the uniform distribution, why we choose uniform between 0 and n. This is because we now have D or D minus 1 fake matches, and we want to make sure that if you consider the minimum weight among these D minus 1 fake matches, so this minimum of those D minus 1 ID random variable, the magnitude should be on the order of constant. So that is comparable with this distribution P. Okay, so basically this shows that the sharp threshold for this so-called almost perfect recovery actually is given by square root of D times BPQ is roughly equal to 1. Okay, so this actually resolved the earlier conjecture in this physics paper. Okay, any questions about this result? Yeah, let me actually kind of give you some special cases to help you understand a little bit more about this result. So in one case is this unweighted model, like when P just equal to Q. Okay, so in this case, basically that means the edge weights are informative, right? P is equal to Q. So the only information comes from the edge connections. Okay, it turns out that in this case, basically the threshold is just D equal to 1, right? Because our previous threshold is given by this square root of D times BQ, right, equal to 1. So P equal to Q, then this Barachek coefficient equal to 1, so it means the threshold just becomes D equal to 1. It turns out that if you're familiar with this like a random graph theory, so when the average degree equal to 1, that's a threshold for emergence of this joint component in order Shanyi random graph. So this actually has some connections to that phenomenon. Okay. Back to the particle tracking problem. So if you plug in these two distributions, do a little bit of algebra, you will find the sharp threshold kappa is 1 over 2 pi. Okay, so that's how we actually get this prediction as shown you earlier. Another interesting model that they're going to focus in this tutorial or in this lecture is this exponential model, where D equals n, again, is a complete weighted graph, but the distribution P is exponential with rate lambda, and then Q is exponential with rate 1 over n. So the mean of this is 1 over lambda, and the mean of Q is n. Okay, in this case, the sharp threshold is given by lambda equals 4. Okay. Yes.
Okay, so about the example of particle tracking, can I imagine the following model? So I have n d-dimensional Gaussians and another copy, which is a perturbed version, and then P will be the inner product between correlated Gaussians, Q will be independent Gaussians, and this will also give the optimal threshold for that model.
No. So that would be different, but that's actually a very nice extension of the model. So it turns out that the threshold will become very different. Okay. Here is this, in physics, they call this mean field model, or like RID weight model. So they kind of ignore the underlying geometry. So that's why they assume that all the edges, like edge weights are RID. But this is definitely not true in the finite dimensional. So that's why what Chen just mentioned is a very nice extension, in the sense that now you really think about, you have n objects, their location, let's say just a Gaussian, or like it's living in a unit sphere. And then in the next frame, they move a little bit, so then you have some new location. Again, they are modeled by some Gaussian vector, for example. And now you don't really need to now come back to talk about P and Q. You can now just study this problem and then try to see in this finite dimension case, then when you can recover this hidden matching. It turns out that the threshold that you're going to see there is very different from this, this mean field model. But I think one thing is that as a dimension goes to infinity, these two predictions will kind of coincide. Yeah. In fact, I'm going to mention some like open or extension of the work. There, I'm going to talk more about this model.
So is this correct that this is only non-trivial when D is dependent on N, right? When D is a constant, it's constant.
Mm-hmm.
As N goes to infinity, you can always have, like, evaluate the model exactly. Is that correct?
Not really. It's just given by this threshold. So even D is a constant, then BPQ can be small, right? So for, BPQ can be large, right? Hold on a second. Like, yes. So then you can still, yeah. So in other words, I mean, so this problem still like can be non-trivial, right? So even D is a constant, yeah. You can still ask about when you can correctly identify almost all the edges. Yeah. Yes.
So the particle matching, you mentioned that the earlier paper had the threshold was off by something.
Mm-hmm. Yes.
So why was it off? Like,
yeah.
Did they know that there was a gap, or what was going on?
Yeah. So I don't know exact reason, but when I talked to the authors, like to Lenka, and I mean before our work, I think she mentioned that at the time, I mean that work is back in 2010. It's actually before they doing the work on community detection, like stochastic block model. So they actually didn't really do the numerical result that carefully. They actually don't know like all these caveats in these numerical experiments. So I think they told me that basically they think that there's some mistake in their numerical results. Yeah, but I think she told me that if they did correctly, then they should give you the precise prediction. Yeah. Yeah.
I'm sorry, when you say then for all M hat, what class of algorithms are you considering?
Yeah, like basically including all the possible estimator, as long as this M hat only depends on the edge connections and edge weights. So you can consider any like estimator. Yeah, so there's no constraint for the estimator for the converse result. For the positive result, we focus on the max likelihood estimator. Yeah, sounds good. Okay, any questions?
When you say they have an error in their numerical experiments, are they performing numerical experiments on synthetic data or in like real particles?
Oh, synthetic data. So they are focused on this model. Yeah. And then what they do is that often they need to give some predictions. So they actually simulate this. So that's, yeah, so their way of so you could possibly simulate the maximum likelihood estimator, right? It's a linear assignment problem. You can solve it, and then you can see actually what's the threshold looks like. What they're doing is slightly different from that. They're actually doing this so-called bleed propagation. And then I think because of something that maybe mess up, so I don't know exactly the reason. It's just based on some informal conversation that I recall, and then that's why they have this kind of mismatch. Yeah, but I should say that their prediction is already pretty accurate. That motivates our work. Yeah. Yeah. In fact, I think in this work, this is a 2020 paper. They actually kind of consider the problem. They actually give a sharp prediction of the threshold. Yeah. Okay, another thing that interesting that I want to talk a little bit is about actually this so-called order phase transition, or so you really basically focus on the threshold and try to understand a little bit more about how this error behaves, or how the overlap behaves. So for this, we actually have a very precise understanding in this exponential model. So remember the exponential model, the sharp threshold is lambda equals 4, right? So when lambda basically is less than 4, then you would expect to have some a fraction of errors, right? Now we're really considering is that let's say lambda is slightly below 4, like 4 minus epsilon, right? And now we can try to understand, okay, then what's the like how the error depends on epsilon, or like how the overlap depends on epsilon, right? So this overlap should be very close to 1, right, as we predicted. But it turns out that we can actually get a pretty tight lower and upper bound. It's actually 1 minus exponential minus some constant divided by square root of epsilon. Okay, for the upper bound for the maximum likelihood estimator. And then for the converse direction, for any estimator, we can show that the overlap is upper bounded by 1 minus exponential minus some different constant C2 divided by square root of epsilon. Okay, so you can see that when epsilon gets closer, this overlap actually converges to 1 really fast. Okay, so roughly the optimal reconstruction error, like 1 minus overlap, is roughly exponential minus some constant divided by square root of epsilon. Okay, so why this is interesting is because, again, from the physics perspective, this is called the infinite order phase transition, because this reconstruction error as a function of epsilon is actually infinitely smooth. So you can take any finite derivative, basically. Okay, so that's why this is called the infinite order phase transition. Okay, so this is actually very rare in these planted problems. So, but before, I'm going to show you a little bit more about these different phase transition order. But before that, I also want to mention that, in fact, we can even categorize the overlap even when lambda is actually any constant between 0 and 4. Okay, so in particular, we're able to show that for the maximum likelihood estimator, as n go to infinity, the overlap will converge to this explicit, not really explicit, but it's a function of lambda, when lambda is between 0 and 4. And this alpha lambda is given by this integral form. And then it turns out that this FGVW that I'm going to explain to you later is actually the unique solution to this system of 4 ODEs. Okay, so I mean, don't actually stare too hard on this, because later I'm going to show you where this come from. So this FGVW basically are some CDF functions, or like complement the CDF functions. But I can numerically solve this system of ODEs, and this is actually this overlap function alpha lambda looks like. Okay, you can see that when lambda is actually approaching 4, the overlap actually converging to 1. Okay, and you can also see that in this part is actually indeed kind of smooth, right? I mean, it's difficult to tell from this numerical result whether it's infinitely smooth or not. But based on our theory, it's indeed actually like infinitely smooth. And these dots actually are the actual numerical simulation results. So it kind of matches pretty well. Okay. Okay, so let me now tell you a little bit about this phase transition order, because this actually connects to these stochastic block models or some other planted models very well. So it turns out that in this stochastic block model, actually the order of phase transition is very different. Okay, so let me just briefly remind you what is a stochastic block model. So basically, you can consider you have k communities in general, right? And then within the community, the edge connections is A over n. Okay, A is some constant. And then across different communities, the edge connection is like B over n. B is a different constant. Okay. So now you can ask the same question, like given this random graph, when you can recover these hidden communities. So this is actually the phase transition picture. I mean, it's a kind of visualization when k equals 2. You only have 2 symmetric communities. So the Sharpe threshold is given by a minus b squared divided by 2 times a plus b. So I think, if I remember correctly, the Sabarata Sen actually covered this in his November tutorial lecture. Okay, it turns out that this is a second order phase transition. So what does it really mean is that this overlap function itself is continuous, right? But if you take the first derivative, the derivative here is 0. The derivative here is positive, right? So the derivative of the overlap actually drops. Okay, so that's why this is called a second order phase transition. Okay, but it turns out that when you have multiple communities, say k is bigger or equal than 5, the picture is very different. They still have some prediction of the threshold, but now once you cross the threshold, the overlap actually jumps from 0 to some positive number directly. Okay, so this is called a first order phase transition because now the overlap itself becomes discontinuous. Okay, so that's why it's called a first order phase transition. Okay, this is in fact why the physics is called a first order, second order, is because they're not really looking at overlap. They're looking at this integral overlap. It's related to this called free energy. When they say first order phase transition, really meant the first derivative of this free energy is discontinuous. So the derivative of the free energy is overlap. So that's why the overlap becomes discontinuous, called first order phase transition. And then the derivative of the overlap is discontinuous, called second order phase transition. Okay.
Is the log k over k just for simplicity or?
Yeah. It's just for it's actually not really for simplicity. So the sharp threshold for larger k is actually unknown. Okay. I think it's only known up to like k equal to 3. So k equal to 4 or 5, so you don't know. But when k is large, the scaling is like log k over k. So that's why I said that some of these are still conjecture, not fully proven. Yeah. There's some other problem. Actually, we know more precisely what's happening. I mean, this here, so I just want to connect back to the subarachnoid sense talk or tutorial. So I think in his tutorial, he mentioned about this spiked Wigner model. I don't know if you still remember. So basically, you can imagine you have a Gaussian matrix Z. You have a rank 1 perturbation given by x0, x0 transpose. And now your observation is y. Your goal is to recover this x0 based on the observation of y. Okay? So in this case, you can also consider x0 to be epsilon n sparse, meaning that there's an epsilon fraction of the entries actually at 0. And now you can also have these two different phase transition, depends on how small epsilon is. So when epsilon is really is actually relatively big, you still have the second order phase transition, as I showed you earlier. When epsilon is very small, then you have this first order phase transition. Okay. But so I should want to say that this is very different from the infinity order phase transition that we observe in this quantity matching model. Yes.
So is there a qualitative difference between these problems and the planted matching problem in the sense that there above the transition you have exact recovery? I mean,
yeah.
But here it's
yeah, exactly. So that's a crucial difference. So here you can see that the phase transition only happens when overlap start from 0 and then become positive, right? In our case, the phase transition is actually the overlap actually how it converging to 1. So that's the difference between of these two different problems basically. Yeah. I mean, you can see that here, if you talk about the overlap is bigger than 0, then there's no phase transition here. Like as long as lambda is bigger than 0, you always get some fraction of edges correctly. Yeah. Okay, another thing that I want to say is that, oh yes?
Is there an underlying reason as to what kind of result you get if you get positive or 0 below the transition? I mean, is there a way you can predict that for various problems, or it's just that each problem has its thing?
Yeah, I don't have a unifying understanding. It's to me, it's more like problem specific. Yeah, sometimes you have this, sometimes you have that. So you really have to look at the problem case by case to some extent. Yeah, I don't see. Yeah. Oh, okay. Let me actually finish this and then we have a break. So basically, another thing that I want to say is that this infinite order phase transition that we observe actually for this exponential model, again, is actually not universal for all different choice of distributions. So for example, in this unweighted model where just P equals Q, so weights are not informative. In this case, it turns out that we can show this reconstruction error is actually not infinitely smooth on epsilon anymore. It's between epsilon to the 8 or epsilon. So it's a finite order phase transition. It's actually a very interesting open problem to determine what's the exact kind of order of this phase transition for this unweighted model. Yeah, I mean, if you're interested, I'm happy to talk about this. So we have some understanding of this, but we're not able to exactly determine the order. Okay. Yeah, I think that's all I want to say about the results. Maybe we can have a break, and then we can come back. I can tell you a little bit more about how we get these results. Okay?
Let's have a 10 minutes break.
Yeah.
All right, so let's get started.
Okay, welcome back. So let's continue. So in the second part, I'm going to show you some analysis of the results. I think I may not have time to go over all of them, but we can see how far we can go. Okay. So the first thing I want to talk about is actually the proof of past result using maximum likelihood estimation. So in particular, as I kind of write down here, basically you want to show square root of d times arbitrary coefficient less or equal than 1, the overlap between maximum likelihood estimator and m star go to 1, right? So let's see how can we prove that. It turns out that this is actually a very kind of standard, relatively proof. In fact, there's often a joke saying that there's only one way to analyze maximum likelihood estimator. I mean, it's not really true, but there's definitely a standard way to think about this. Okay, so let me actually first draw some picture to help you to understand what's going on. So basically, the idea is the following. I think maybe you actually are familiar with this, but let me just draw this picture to make sure you understand that. So you can draw a kind of visualization, like M star. This is the true kind of matching that you want to recover, right? You can now think about the space of all the possible matchings in terms of distance to this true matching, right? So for example, like in this case, since you want to show the overlap is very close to 1, you can draw a bar of the distance. Maybe let's say like it's 2 beta n. So in terms of the difference in terms of edges. So here is actually all the matchings where the cardinality of the symmetric difference is actually less or equal than 2 beta times n. Okay? And now basically what we are trying to show is that for all the other matchings that are far away from these true matchings, its likelihood should be smaller compared to the true matching. Right? If we can show all these matchings here have a smaller likelihood than the true matching, then we know the maximum likelihood estimator has to be in this part, right? And then that means the distance between 2m star has to be smaller than 2 beta n, right? And then if you can make this beta to be small, like vanishing, then you show the overlap goes to 1. Does it make sense? So basically, that's why the key thing is that we want to kind of show the likelihood in this gray part, like shaded part, has a small likelihood than a true matching. And then how to do that? Sometimes people call this like Peeling argument, but really it's like you consider a particular distance, say 2t, right? And then you can think about t is actually bigger than beta n all the way maybe to n. And now for each of these like possible distance like 2t, you want to show the matching at this particular distance has a smaller likelihood than m star. So how to do that? You basically divide into 2 steps, like as I'm showing here. So the first step is try to count like how many such matchings here there are, right? Okay, that's not that hard. You look at all the possible matchings with like 2t different edges. So that's just saying that you have your true matching. You basically pick like n choose t as a subset of nodes, and then you just reconnect those nodes. Right? So that's why you have n choose t times t factorial, many of them. It's an upper bound. I mean, you can make it precise, but this upper bound is already enough. Okay? Now, the second thing is that you fix a particular matching with distance t, and you want to ask, OK, what's the probability of this fake matching m has a higher likelihood than m star? OK, this often boils down into some large deviation analysis. So basically, if you compare the likelihood, basically, if you look at the difference of the likelihood, you will boil down into 2 parts. The first part is actually the blue edges, actually those edges not on the matchings. You basically want the sum of the log likelihood weights of the blue edges to be bigger or equal than the sum of all the log likelihood weights for the true edges and stuff, right? If this blue part is bigger than the red part, then you know the true fake matching M has a larger likelihood than the true matching M star. Does it make sense? Okay, and now how to estimate this? Well, you're basically just using some large deviation. The first thing is that you want to make sure all those edges in this like M/M star should appear in the graph, right? And then each of these blue edge appear with probability d over n. Remember? So then that's why you have d over n to the t, because you need a t such blue edges to appear. Okay? And now on top of that, you also make sure the log likelihood weights to be bigger or equal than log likelihood weights of the true edges. So this one, you can just plug in the Chernoff bound. And that's where this Baer-Cherry coefficient comes from. Okay, so in fact, I will give you a practice problem after the lecture. Basically, you will show that this Baer-Cherry coefficient is nothing but some Chernoff bound. Okay, so then you have this probability estimate. Then you can just combine these two together, basically taking a union bound. So remember, this is actually the probability that we want to upper bound at the begin with, right? We want to make sure there's, like we want to upper bound the probability there exists a matching that is far away from the true matching, has a high likelihood than M star. This is the upper bound thereby take the sum of t. So we're considering all these possible distance t bigger or equal than beta n. This is actually the number of such matchings. N choose t times t factorial, and this is the probability this particular matching beats the true matching, right? Okay, now the crucial thing is that this one, you can roughly upper bound it by n to the t, and then this will cancel this n to the t here. This is actually d times b squared, like pq come from. And if this is less or equal than 1, like strictly less than 1, then this sum already goes to 0. If you just properly choosing some beta little n. It turns out that you can do slightly more precise calculation. So even when this square root, like this product equal to 1, you can still show this sum actually go to 0. Okay, but that's not that important. Okay, so it's basically just coming from this union bound analysis. Okay, makes sense? And then this also kind of give you a hint like where this condition come from. Any questions? I mean, feel free to let me know if you want me to elaborate a little bit of the particular step. I mean, so I'm happy to do that. But if you feel okay, then I will continue. But yeah.
Can you explain the main inequality again? So now you fix a matching M, and then you want to compare it with M star, right?
You mean this one?
Yes.
Yeah. So basically, what I'm trying to say is that you have two parts. One is this d over n to the t part. Is that okay with that? Because you want the edges in these blue edges to appear in the graph, right? You like M/M star. So you basically have t such edges. You want them to appear, right? Each of them appear d over n with probability. So that's why you have d over n to the power of t. And now this part, what I really meant is the following. Like this BPQ is like you can think about. Let me rewrite here. So this is a generic statement. Yeah, so this BPQ part actually come from this basically this large deviation analysis. So here, think about you have a bunch of ID random variables. So the xi is actually ID according to this log likelihood ratio on the distribution P. Okay, and then the yi is actually the log likelihood ratio under distribution Q. So you have these two sets of independent random variables. You ask what's the probability of the sum of yi actually is bigger than sum of xi. These should be small because the xi actually has a positive mean if you do that. Y actually has a negative mean. So that's why you would expect this probability to be small. You can ask how small it is. Then this is given by the Baer-Cherry coefficient to the power of 2t. How to get that? just plug in the Chernoff bound, optimize the tuning parameter, you will get this. Yeah. Does it make sense? Okay, so I hope that you got this. This is actually, like I said, this is the most standard way of analyzing max likelihood estimator, but it's actually used very often in many different problems. So, especially for many problems in this graph setting, so this often gives you a very good result. Another thing that I want to say is that from this expression, you can also see that when dB squared PQ goes to 0, you can actually further show this, so you can further take this t to be bigger or equal than 2, or like 1. So this entire sum will go to 0. So that means you can show that this max likelihood estimator has to be exactly coincide with M star with high probability. So this is actually often in the literature people call it exact recovery. So in fact, this should be the exact recovery threshold. It's just like a side note. Okay, so now I'm going to talk about the proof of negative result. This turns out to be much more challenging, so that's actually something that I'm going to focus on next. So why negative result is challenging? Well, one difficulty comes from the fact that the max likelihood estimator may not maximize overlap. Okay, so the max likelihood estimator, we know that if the prior is uniform, this will minimize the probability of error. But here we're looking at the overlap. So the max likelihood estimator may not maximize overlap. So we can't really just show the max likelihood estimator fails. Okay. It turns out that the optimal estimator is given by this maximum posterior marginal estimator. So it's basically the optimal estimator is given by the following. Let me write down here. So the optimal estimator is actually given by, let's see. So you basically look at the probability of a particular edge, let's say. Okay, and then given the observed graph, I'm using W to denote the observation. Okay, so if this is bigger than 1/2, then you actually okay, then you put ME equal to 1. And if it's less than 1/2, then you put E equal to 0. Okay, so it's basically like just try to compute this so-called marginal probability. So if you have your observation for every edge, you compute what's the probability of this edge will be in the planted edge. Okay, if this probability is bigger than 1, then you put it in your estimator. If it's less than 1/2, and then you actually do not put it. Okay. But one thing that you will see that to compute this marginal posterior, then you have to look at this so-called posterior distribution. Let me actually first talk about this posterior distribution. So the posterior distribution is just it's actually in this case is a Gibbs measure over all the possible matchings. So this is a distribution is given by exponential, and then here is nothing but the sum of the log likelihood weights for this matching. Okay. And then the marginal, that is just take this high dimension distribution, and then you just take a bunch of summations, and then you will find what's the marginal probability of a particular edge is in the matching or not. Okay, and then the optimal estimator is just given by the one that I was showing there. Okay. One thing I want to say is that when P equals Q, like in this unweighted case, for example, then this P equal to Q, this is just equal to 0, right? So then that means this posterior distribution is just a uniform distribution over all the possible perfect matchings. Does it make sense? So like in the case where the edge weights are informative, then the problem just basically boils down to look at like the posterior distribution just becomes a uniform distribution over all the possible perfect matchings in this observed graph. Okay, and then the hidden one is actually one of them, right? And then you want to ask, okay, can you actually identify the edges on this hidden matching? Okay, so But more generally, you have this posterior distribution. So as you can see, one difficulty of directly analyzing the maximum posterior marginal is because you need to do marginalization. You need to sum up all these different possible matchings. So that often requires like n factorial or like close to n factorial summation. So that's why it's a difficult to directly analyze optimal estimator. Okay. So our first idea is that it turns out that we don't have to look at the optimal estimator. We can actually look at the so-called posterior sampling estimator. So it turns out that we can just sampling from posterior distribution, and we can show that this is optimal within a factor of 2. Okay. So what I mean is that you have this posterior distribution, right? You just imagine you have a way to sample one matching from this posterior distribution. Okay, and then using that matching as your estimator. Okay, so this may not be the best estimator, but we can show that in terms of error, it is actually at most twice than the optimal error that you can get. Yes?
So if you do that estimator, you're looking at each edge separately, right?
Yes.
And
yeah.
if you put all those edges together, you may not have a matching.
Yeah, exactly. So this estimator may not actually output a valid matching. So because the estimator that we're saying may not be even like a valid matching. It's just a bunch of edges that you believe they are in the matching. Here, the cardinality even may not be n. Like you may actually output more edges you would believe that are in the matchings. Right. So this is actually more generic. Like, yeah. But this posterior sampling will always give you a valid matching. Okay. And then this shows that this is optimal within a factor of 2. So let me actually show you the result. This is actually one of the kind of the key, so the simple one, but it's actually kind of very crucial. So let me actually slow down and tell you what's the idea. Okay, so you basically just take m tilde to be a matching drawn from this posterior distribution. Okay, and now let's first look at this. You want to actually upper bound the error in terms of m tilde and then difference to m tilde and m star, right? Okay, and now I can always do this triangle inequality by plugging any estimator m hat, right? So that's generic. I can always do that. Okay, now here's a magic thing. So it turns out that these two expectation is the same. Okay, so this, why is that? So this is the same thing, like something I talk about here. Okay, it turns out that for any estimator, m hat, if you look at the joint distribution between the two matching m star and m hat, this joint distribution to be the same as m tilde and m hat. Okay? Okay, so why is that? So one way to understand this is that you can first, suppose you draw m hat. Okay? Now, you first actually draw the weight, w. Okay? And then the m hat will be given by the weight, right? So m hat is already done. Now, given the weight, how you generate m star? Well, we know that according to the model, if you fix the weight, then m star also going to follow the posterior distribution. Does it make sense? Right? So then that's why if you look at m tilde, that's the same thing, right? So I fixed w. M tilde is also drawn from the posterior distribution. So that's why these two joint distribution have the same.
Is a condition on the weight then?
Yeah, I mean, I want to think about into 2 steps. So the joint distribution can be written as the distribution of the weight, and then the condition distribution of m star, m tilde conditional weight. So the distribution of the weight is always the same, and now the condition distribution of the weight and the m star, m tilde are the same. So that's why the joint distribution is the same. Does it make sense? So in fact, this is people in physics. People call this so-called Nishimori condition. So they actually have this name. Let me actually write it down. Because if you read some physics paper, they will always say something like this. Yeah, it's just nothing but some Bayes rule to some extent. Like basically just saying that if you fix the weight observation, the ground truth is just follows from the posterior distribution. Okay. Okay, so now if you understand this, then that's not that hard to see these two expectations the same. right? Because they basically, the joint law are exactly the same, so that's why it's 2 times the expected value of the distance between m hat and m star. Okay, and you can see that then that means the error of the posterior sampler is at most twice of the error of any estimator. Okay, so now for our purpose, if you can get a lower bound for this posterior estimator, sampling estimator, then this will always give you a lower bound for any estimator m hat. So that's why it's enough to show some error for this m tilde. And then you at most away by a factor of 2.
Sorry, now your question. So is m tilde also a valid estimator, right? M tilde.
Yeah, m tilde is a valid estimator.
You replace m hat by m tilde in that equation.
M hat, m tilde. Okay.
Does that make sense? So m star m tilde is equal in law to m tilde m tilde.
That's probably does not make sense.
So what am I missing here?
Oh, okay. Yeah, unless you're changing m hat to be another independent sampler. So, yeah, right. Yeah. So m tilde is actually independently drawn from the weights. Does it make sense? So you can change m hat to be another independent sampler. So that's fine. Yeah. Okay, sounds good. Okay, so now because of this, then our task just reduced to analyzing the posterior sampling. Okay, so now how to understand this posterior sampling? Again, we can using this kind of visualization to help us to understand what's going on. So you can see that I put m star at the center again, and then I draw a ball of a distance delta n. So you can think about the matchings that are close to m star. And then the gray area are those matching that are far away from m star. Okay, so basically I can try to show the 2 different things. One is that I can try to upper bound the posterior mass of the matchings within this white region. I kind of normalize by the posterior probability of m star, but this normalization is not that important. It's just that now I can look at the ratio. Now if I can show this ratio, like it's upper bounded by exponential some constant times epsilon times delta times n. Okay, I mean this 7 is not that important. And now if I can also lower bound the posterior mass of the matching that are far away from m star. Okay, again normalized by the posterior probability of m star is bigger or equal to exponential 14 epsilon delta times n. Okay, if I can show both, then what does it mean? Okay, that means you have exponentially more posterior mass in the gray region compared to the white region, right? So then that's why if I just randomly pick, like sample from one matching from this posterior distribution, then very likely I will land in this gray part. Does it make sense, right? Because the posterior mass here is much more than posterior mass here. So if I draw a sample matching from posterior distribution, very likely will land in this region. Okay, and now since it lands in this region, then the distance to the m star is at least delta n. Right, so that shows that the posterior sampler estimator will have a difference like distance at least to delta n. Okay, if I can show both of these 2 holds. Make sense? Okay, so the proof of the first part actually is relatively straightforward. So, I mean, the idea is the following. So it's again like this Maxine-Lacour estimator that I just presented. The crucial thing here is that if you look at the matchings in this white region, there are not many of them because they have to be very close to m star, right? M star is kind of fixed, right? So if you look at this, there are not many such matchings. And also, since those matchings are close to m star, I mean, their likelihood cannot be too big or like too large compared to the true matching. So that's why you can upper bound this quantity basically using the first moment method, considering all the possible matchings, like close matchings, and then bound each of the term. So you can compute like the mean of this, and then show this mean is bounded. There's only one caveat, as I say here, you need to do some proper truncation, because sometimes you will have a matching that is, in terms of this ratio at least, will be much bigger than 1. But then those matching actually will not occur very likely. So you're going to kind of rule out this real event, and then to control this part. Okay, but I'm not going to the details. It's just more like some technical detail here. But the idea here is relatively standard. Okay, so I'm going to focus on the negative part. It's actually much more challenging, because often if you want to prove a lower bound, it's always like in this case, it's harder in the sense that you cannot just bound the expected value anymore, right? You probably need to use the second moment method. So here, what we are trying to prove in this second part is actually constructive, in the sense that we're actually going to show you that we can find like exponentially many matchings in this gray region. Their likelihood is actually indeed bigger than m star. Okay, and then if we can do this, then definitely this ratio will be big. Okay, so now the question becomes, how can we find such exponentially many matchings whose likelihood is bigger than m star? Okay, sounds good. Okay, so now let's actually see how can we do this second part. There's actually some useful way to actually think about the difference between matching and then versus a true matching using this so-called alternating cycle. So this will be useful. In fact, this is actually quite common terminology in this bipartite matching literature, right? So basically, if you look at m star, so that is just, for simplicity, m star is just given by these solid lines. And then m is just any matching given by the dashed line and also 4 and 4 prime. And then you can look at the difference, right? And in the difference, you can see that you will have these like alternating cycles, right? So here, I use the red edges to denote the edges on the true matching, and the blue edges are the edges not on the true matching. Then you will see this cycle alternate in colors. Okay, make sense? Okay, so why this is useful is because now if I remember, my goal is to construct these exponentially many matchings where the likelihood is larger than the true matching. But now I can just look at the difference. Now this boils down to find exponentially many like long cycles or like alternating cycles. They are so-called augmenting, in the sense that if you look at the log likelihood, sum of the log likelihoods for the edges, like on the blue edges, is actually bigger than the sum of log likelihood rates of the red edges. Okay, so let me actually pass a little bit. First thing is that you want them to be long because you want to make sure those matchings are far away from the true matching, like in this gray region, right? Like here, right? So then that's why you need this alternating cycle to be long, so then they are quite different, right? And then second thing is this augmenting is because if this is true, then that means, they actually have a common part of this true matching and then the fake matching. So like all those edges, they share in common, right? So if you take those, some of them, then these become the total log likelihood weights for the fake matching, and it will be bigger or equal than the total log likelihood weights for the true matching. Make sense? So now this just boils down to find this long alternating, like augmenting cycles. Okay, let me actually show you some computation, at least to tell you a little bit like why this is, like where is this difficulty. So one thing is that the augmenting alternating cycles are rare, okay? Because for this to happen, we know that this is a small probability event, right? Like in fact, in our first moment, like in the maximum likelihood estimator analysis, we actually show this probability is upper bounded by the Barachayi coefficient, that kind of stuff, right? So each of those, so that's why this augmenting property is rare. But the good thing is that we have many such alternating cycles to consider, right? So hopefully we can still find like many. So how to do this? Well, so a very natural way to do this is use this so-called second moment method. So the first thing that you want to do is that you can try to compute the expected number of such cycles. Okay, so I want to show you some computation here just to illustrate how this works. Yes, okay. Okay, so one simple calculation we can do is for computing the expected value, right? So let's say I focus on like SL. SL just means I look at all these alternating cycles of length, say 2L. Okay, and I want to calculate what's the expected value of that. Okay, so how to do that? Well, this is you first like count like how many such alternating cycles to consider, right? So that one is like n choose L, right? And then very precisely, there's this notation like it's like an inverse of L factorial because you want to get rid of this fixed point, right? But then basically, this is roughly the same as roughly like n to the L. You can consider that. So that's like how many to consider. And now you also need to consider what's the probability of augmenting, right? Okay, that one we just so we have an like estimated, so I should not say equal, like approximated. That one, if you remember, we actually approximated by d to the n, and then bpq squared to the power of n, right? Again, this is an upper bound, but really here we need a lower bound, but there's a way to turn, I mean, if you believe the trainable bound is tight, there's often a way to turn this upper bound to a approximately lower bound, right? Okay, so now you do the computation. This is the same computation as we did before. Then you have this to the power of n, right? Okay, and now we are in the negative, proving the negative result. So this should be actually bigger or equal than 1 plus epsilon, right? So that's the negative result that we want to show. Okay, now this whole thing now grows as exponential epsilon times L, right? And then L will be chosen as some constant times n. So that's why you would definitely have exponentially manage them on average at least. Okay, make sense? Okay, so that's not that hard, right? So that's okay, but now, I mean, if you can further show the second moment is actually upper bounded by some constant times the mean square, then you can use for example, this Paley-Zigman inequality, and now you can quickly conclude that this cardinality of S is indeed actually exponentially large with constant probability at least, right? But now it turns out that for this problem, this is actually not feasible approach. The reason is that it turns out that the second moment is actually much, much larger than mean square. Okay, the kind of a high level interpretation is that the reason here why this second moment is much more larger than mean square is because you're looking for long cycles, right? Remember, we want this matching to be far away from the true matching, then we need this cycle of length is like constant times n. If you randomly pick two such long cycles, they're going to overlap quite a bit. And this overlap will induce some correlation, basically. I mean, that's the short answer. But I mean, if you really want to see this, you need to do the computation. You will see that this is impossible to do. So that's why the second moment method is nice, but it doesn't work in this particular setting. So that's why we need some new idea. Okay, so here is actually our new idea. Basically, it's like, let's not try to find this cycle in one shot. So instead, let's try to break it into two steps. Okay, the first thing is that, remember we talked about these long cycles are kind of correlated because they tend to overlap a lot, right? So why we don't just start from short paths? Okay, if we can find many disjoint short passes, and then in the second step, we can try to piece them together, like connecting these paths into long cycles. Okay, so this idea is called a sprinkling idea. It actually appears previously in the random graph literature, but for different purpose. So let me actually show you some visualization, at least to show you at a high level. So how does this two-step cycle finding scheme works? So the first thing is that we need to reserve a small fraction of the vertices. Okay, those vertices will be used for sprinkling. like in the second stage. And now in the stage 1, I'm going to use all the vertices, like non-reserved vertices, like in V complement, and try to actually somehow find many short disjoint, like augmenting, alternating passes. Okay, the length will be a constant level, and then my hope is that I can find like a constant times n many of such short passes. I mean, later I'm going to tell you how we achieve this, but suppose you get that. Now in the second step, I'm trying to do this so-called sprinkling. So I'm trying to connect these passes into long cycles now using the reserved vertices. Like for example, as I shown here, there's some, I mean, this is just some visualization, but through some reserved vertices, you may be able to connect these different passes. And now if you can do this, then at least, for example, this one give you one possible alternating pass. Okay, but there are several caveats. The first thing is that you want to make sure the alternating, like indeed they're still like alternating in colors, right? You don't want to destroy that. The second thing is more technical, is that these passes are augmenting, right? But then these sprinkling edges may not be augmenting. So somehow you want to make sure that the weights here actually going to dominate the total weights of the entire cycle. So those sprinkling edges, they are not, I mean, their weight contribution are kind of negligible. So then indeed, in the end, you still get an augmenting, like alternating cycle. Does it make sense? Okay, so next, let me tell you how we can actually construct this. I'll keep track of time. Okay, this cycle finding scheme. Okay, so this is actually a kind of breakdown into a specific steps. So in the stage 1, so what I'm going to do is that I'm going to actually use the non-reserved vertices and then try to find like these many like augmenting, alternating passes. So LK actually a bunch of left nodes, for example, and then RK are the bunch of nodes, like right nodes. And I want to make sure that between LK and RK, for every vertex in LK and RK, there will be like some augmenting, alternating paths connecting them. Okay, and I want to do like construct many such pairs. So I need like a capital K to be like on the order of n. Okay, so that's the kind of the precise way of the first stage. And now in the second stage, I do the sprinkling. Let me actually draw a simpler visualization. Let me just focus on 2 pairs. Okay, so they are connected, like every vertex here are connected by some augmenting, alternating passes. And now I want to connect them. So how to do that? Well, the first thing is that I'm going to use these reserved vertices. Okay, and then these non-reserved vertices will have some blue edges connecting to these reserved vertices. So that's where I get this U1 prime, and then V1, and then U2 prime, and then V2 through those blue edges. And now this U1 prime will have their counterpart through the red edges, right? So that's U1 and the V1 prime, and U2 and the V2 prime. Make sense? And now the last step is that in this example, I want to actually somehow U1 is connected to V2 prime, and then U2 is connected to V1 prime, so I can complete the cycle. Okay, so if I can indeed find some blue edges connecting some node in U1 to V2 prime, and then some node in U2 to V1 prime, then I can highlight the alternating cycle that I found. So for example, I can start from the node U1, go back to U1 prime, go to L1 through this long augmenting, alternating paths, and then to V1, V1 prime, and then through this long crossing edge, and then continue this way, and then return back. That makes sense? Okay. So now really the key thing is that how you can ensure like these long crossing blue edges will occur. Okay. So to do that, you can simplify this a little bit. So basically, we use this so-called supergraph representation. So I'm going to consider this as a whole, and then this as a whole, this as a whole, and this as a whole. So I will have this kind of a graph. Okay, so this one just means this entire, like this part. Okay, and then 1 prime. So there's already there's an augmenting alternating path connected them. Similar thing for 2 and 2 prime. The only thing missing is this 1 to 2 prime and 2 to 1 prime. Okay. Okay, so by doing this, definitely if you can find alternating cycle on this supergraph, then you can go back and expand it to the augmenting alternating cycle in the original graph, right? Just using the construction. The second thing is very important is that we're going to ensure this supergraph is so-called supercritical. So in the sense that the average degree of this node is actually much bigger than 1. And then, okay. And then because of this, if they are supercritical, then we know that in this supergraph, you can find like a long alternating cycles. Okay, so in the third step, we're going to show that this supergraph will contain many, actually exponentially many alternating cycles of length on the order of n. This actually is basically some standard depth first search argument. Because this graph, the average degree is so high, you can try to kind of using some greedy methods, starting from one node, look at it and pass, and then just continue in this fashion. Okay, and then you can try to find many long alternating cycles in the supergraph. Now the crucial thing is that you want to make sure the supergraph is critical. Okay, so what does that mean? That means you need the degree to be large, right? So the degree will depend on how many nodes really are in here. It's like the size of the joint node here. Okay, and it also depends on how many such nodes you can construct. Okay. Okay, so this is actually how we actually really construct this first stage, like this non-augmenting alternating path. The idea is that we can basically use this so-called neighborhood exploration process. Okay. So we basically start from one node and then try to grow a left, like a tree from the left-hand side. Okay. And then we can also, remove the inspected vertices and then grow a right tree on the right-hand side. Okay. And then this is the LK and the RK that I showed you in earlier. And you can see that every node in LK will be connected to every node in RK through some like a augmenting alternating path. Okay, but now there are some challenges. The first thing is that, remember, we wanted the supergraph to be supercritical. So we want to make sure these LK and RK to be large, so they are easier for the sprinkling stage. Okay, and also we want to have many such LK and RK. Okay, so that means we want to make sure that when we do this tree neighborhood exploration process, we're not using too many vertices. Okay, because every time when we do this exploration process, we find this LK and RK, and then we're going to remove all these inspected vertices. And then on the remaining graph, and then we're going to find another one. And just continue this fashion. So for this to actually find many such LK and RK, we want to make sure every stage we do not use many vertices. Okay, so how we exactly do this? It turns out that, one natural way just do the standard branching process, like just starting one edge, look at the neighbors, look at the neighbors' neighbors, and so on and so forth. So that's a standard way. But then it turns out that if you follow that way, you will use too many vertices, because you also want to make sure the passes are augmenting. So the idea that we have here is that we break this branching process, or like the breadth first search, in different epochs. So here we have 1, 2, and then 3 epochs. Each epoch actually has a certain steps, like a capital H steps. Okay? So then the crucial thing is that at the end of each epoch, if we already found this path is not augmenting, then we're not continuing to grow anymore. Because we already know that there's no way for this entire path to be augmenting, so let's not actually continue to grow, to save some vertices. So in other words, we only look at those leaves whose paths to the root are indeed augmenting, and only grow from there. So that will help us to actually save the number of vertices used. Okay? And now if you look at this entire epoch, So this is, you can view this as through different epochs. This is like a branching process where the average number of offsprings is given by this. Why is the case? It's because you have h steps. So the total number of offsprings here should be like d to the h, right? And then again, we already know that the probability for these paths to be augmenting is just the Baratari coefficient squared to the power of a number of steps, right? And then again, because we're in the negative direction, this is bigger than 1 plus epsilon. So this is can be, if you choose h to be large, this is much bigger than 1. So that's why we have a supercritical branching process. Okay, so that's why we can imagine this process we're going to continue until we find enough actually desired augmenting passes. Okay. Yeah, I think that's all I want to say for this entire construction. Okay, sounds good. Yes.
So, which vertices here are the L and R?
Oh, okay.
Do
Fair.
they only contain the bottom?
Yeah, only contain the bottom.
Oh,
Only contain the bottom.
But
That,
how about in the middle leaves? Do you just ignore them?
yes, in our actual construction, we just completely ignore them. I mean, the reason why we can ignore them is because often in this branching process, actually the number of nodes is going to dominate it by the last layer. Yeah, so that's why it's okay to ignore them. And also another thing that why we look at the bottom is good is because now we have a long augmenting passes. Because if you start from the middle, then the length to the root may be smaller. So if you only select the last layer, you can ensure that the depths, for example, if you have L epochs, the depths will be h times L. So you kind of, yeah, so that's why we kind of focus on the last layer. Okay, sounds good. Yes, okay. Let me just use a little bit, yes, question?
I have a very, very high level question. So your in the positive case, in the upper bound, your proof was fairly straightforward, right?
Mm-hmm.
In the lower bound, you have to come up with the construction, and it is like more involved. Is this common for these kind of problems? That lower bound is much harder than the upper bound?
Okay, depends. So for this problem, it turns out that the lower bound is harder. There's actually some simpler approach. In fact, I think in the next lecture, so I'm probably going to mention that. There's an approach based on information-theoretic method called a mutual information argument. That one actually is much simple to implement. But unfortunately for this problem, that method won't give you the sharp like a threshold. Yeah, so I think depends on the problem again. And sometimes the positive direction can be also hard. Depends on exactly what's your goal here. So in this problem, we look at this like almost exact recovery or almost perfect recovery. We want the overlap converging to 1. For some other problem, like for the stochastic blocker model, as you mentioned earlier, the phase transition happens when the overlap is actually go from 0 to positive. So in that case, positive direction is actually much harder to like establish because you cannot just rely on analyzing max likelihood estimator anymore. That probably won't give you actually the sharp threshold. So I guess the short answer is that it depends on the problem, depends on the specific performance metric they're using. Sometimes the positive direction is harder, sometimes the negative direction is harder, or sometimes both are hard. I would say, but it's very rare both directions are easy.
Then you won't write a paper.
Yeah.
I have one more question.
Sure.
I'm a little confused about the exact
Yes.
the exact recovery. So for us, the objective is to find a matching where the overlap is very high, and in the limit, the fraction is going to 1.
Yes.
But exact recovery means that even the pre-limit, you should find the exact matching. Is that correct?
Okay. It's basically the overlap will be exactly equal to 1.
Equal to 1.
Yeah, with high probability.
I see.
Yeah, so it's the probability of the overlap equal to 1 goes to 1.
I see.
Overlap, yeah. yeah,
And
I think.
the threshold is like drastically different.
Yes.
B times B square is 1 versus 0.
Yeah, exactly.
I see.
Yeah, exactly. Very good point. Okay, I guess due to the time constraint, I probably won't bother to talk about this anymore. But so the short answer is that for the exponential model, if you want to get this very tight, like dependency on epsilon, you have to do something more. And this is actually also quite interesting, but it's very different from the one that I just mentioned. Yeah, let me skip this. And then there's also a part about how we get this exact overlap using ODE. I think, yeah, I don't have time to talk about that. Yeah, but basically the idea is that there's a connection to this so-called cavity method or like objective method or local weak convergence theory. Yeah, but let me actually summarize this a little bit. So I think in this lecture, we at least seen like, so I talk about this sharp threshold, okay, and I also show you this infinite order phase transition phenomena. And then the key idea for proving this is using this two-stage cycle finding idea. And then like the high-level reason is that you're looking for long cycles. So that's why the second moment method often are very difficult to implement. So that's why I want to break it into 2 stages. Okay. This fourth bullet, I actually don't have time to cover it. Here actually are the reference papers for this lecture. So the first paper actually talk about this ODE characterization. The second paper actually talk about this how we get this sharp threshold and infinite order phase transition. Let me maybe use 1 or 2 minutes to talk about this a little bit of the open problem, because this is probably very interesting. So one thing that I'm interested about, actually, I don't know how to do that. I mean, so I tried it very hard, but I think there is a potential promise to do that is that can we get the optimal error as a function of, say, in the exponential model, like this lambda, for actually optimal estimator. Remember, like the exact characterization we give is only for maximum likelihood estimator, which may not be optimal, right? So if you look at the optimal estimator, you should possibly get a better, like a smaller error as a function of lambda. So how to do that? There's actually one method in statistics physics and computer science called interpolation method. I think in particular the Will Perkins here, actually he's an expert on this. So this actually, might be an opportunity to use the interpolation method to prove this like an optimal error as a function of this parameter. Okay. Another thing that is very interesting is that there's an extension to this so-called planted k-factor model. K-factor just means spanning k regular graph. So k equals 1 is just a matching. And k equals 2 is like you have like a spanning 2 regular graph. So it's like a bunch of disjoint cycles, I think. Okay. So you can also consider that. There's actually a very nice extension of the conjecture. Is remember when k equals 1, so that's our like the one that we talk about. But for k-factor, just times square root of k. So the positive direction is actually relatively easy to show. You can again analyze maximum likelihood estimator as we did. You can get this, but the negative direction is still open. Okay. There's also extension to these very interesting so-called k hypergraphs. So remember here we just look at this normal graph, but you can consider hypergraphs. And a very interesting observation in this physics paper is that now you will actually observe first order phase transition when k is bigger than 2. So when k equals to 2, we have infinite order phase transition, but when k is bigger than 2, you get a first order phase transition. It's still a conjecture, but I think this might be possible to prove. I think this fourth point relates to Chen's earlier question. If we take the geometry back, then we should consider finite dimensional Euclidean space. So like every particle or node will have associated with some finite dimensional vector. And then you can try to, based on that, try to match them. This is also related to this perfect so-called planted feature matching, because you really now can think about each node has some feature vector like associated with it, right? And then you have another bunch of nodes where have some perturbed feature vectors, and now you want to see how you can align them. This is also called a database alignment problem. And then the last point is that you can also consider some other planted structures. For example, I think 2 interesting cases, spanning trees, or the traveling salesman, or like salespeople. Okay. So I think those are quite interesting open problem I want to mention. Yeah, if you're interested in any of this, just feel free to talk to me. I'm here during this week, so I'm happy to talk with you more about that. Okay, yeah, thanks.
Right, thank you.
I guess like, is there anything known about just regular graphs, not necessarily bipartite, like just plant a perfect?
Oh yes, yeah, that's a very good point. In fact, I think all the results I talk about here actually not really pertain to this bipartite graph. You can also consider unipartite. So the results will be, I think, will be the same, and then the analysis also go through. So we just focus on the bipartite version because of the application, and also it's maybe slightly easier to present. But I mean, there's not, yeah, the bipartite part is not that important. Yeah, but that's a good point. I forgot to mention.
Okay, great.
Yeah.
So let's reconvene tomorrow at 10 a.m.
Yeah. Thank you.